differentiable as many times as you like. And the derivative at 0 equals 0 for all n. Okay? So why do I bring this up? Because then the Taylor polynomial for this function that I've written here at 0, so this is the Taylor polynomial at 0, just equals, again, the sum of the derivatives evaluated at 0 times x minus 0 to the k, but all the derivatives are 0. And thus, the function is in fact equal to the remainder term near 0. So you see the remainder term carries all of f, so it doesn't necessarily need to be small. Okay? And what I'm trying to say is that in general, you can't just throw away this remainder term and expect that to be even near the point x, some sort of faithful representation of the function just by the Taylor polynomial. Because as we see for this function, the Taylor polynomial is identically 0. If I throw away the remainder term, I would be saying f is 0, but it most certainly is not near x equals 0. Okay? So that was the point of that discussion. So now let's give the proof. And as you see, we're just going to kind of apply the mean value theorem repeatedly to higher derivatives of f, but not necessarily of f, but of a function we cook up out of f. So let's take 2 points, x0 and x, not equal to each other. Of course, if they're equal to each other, we can take c to be whatever we want, because then because then what we pick up is f of x equals f of x on the right-hand side. So we can just consider the case that x0 does not equal x. Now let m be, so this is just a number depending on x and f0 over x minus x0 to the n plus 1. Okay? So p sub n, this is again the Taylor polynomial of degree n, f of x minus p sub n of x over x minus x sub 0. So this is just a number depending on x and x0. Then just rewriting this, this means that f of x is equal to p sub n of x, the Taylor polynomial of n at x, plus mx times mx x0 times x minus x sub 0 over n to the n plus 1. Okay? So now the goal is to show that, in fact, this number can be written as the n plus 1 derivative evaluated at some point over n plus 1 factorial. Okay? So now the goal show there exists a C in AB such that mx equals f n plus 1 over C over n plus 1 factorial. Okay? Okay, so now what is what is this defining characteristic of this Taylor polynomial at this nth order Taylor polynomial? Evaluate with respect to x0. Well, the point is that this Taylor polynomial agrees with f at x0 up to nth order, up to n derivatives. Okay? In other words, if I take the kth derivative of f and evaluate it at x0, this is the same as taking the kth derivative of the Taylor polynomial and evaluating it at x0. So the Taylor polynomial agrees with f up to n derivatives at the point x0. All right, so again, this is the whole point of Taylor polynomials, is that they, at least at the point, agree with f up to nth order. Okay? Doesn't mean they agree with f or even are a good representation of f away from x0, like we just saw. But at least at x0, they agree with f. Okay? So now I'm going to define a new function, which I'm going to start applying the mean value theorem to, and hopefully come up with this c. It's g of s equals f of s minus p sub n of s minus this number from earlier times s minus x0 to the n plus 1. Okay? And something to note is that this function here, so this whole function, so g, first off, f is n plus 1 times differentiable. This is a polynomial, so it's n plus 1 times differentiable. And this is just a polynomial also in s, so it's n plus 1 times differentiable. So in s. Okay? So let me draw a picture. So we have x0 and x. At least in the picture, x is bigger than x0, but that doesn't really matter. So what do we know about g of x0? Well, this is equal to f. And now when I stick in x0 here, I get 0. So, and now f of x0 minus p n of x0, again by this first thing here, for k equals 0, this is equal to 0. Okay? And now what do I know about g evaluated at x? This is equal to f of x minus p n of x. Remember, the variable that I'm changing, or at least the free variable there, is s. So if I stick in x, I get f of x minus p n of x minus m, this constant from earlier, which I chose depending on x and x0. But using this relation here, this is 0. Okay? So I have that the function g at x0 and at x is 0. So by the mean value theorem, or Rolle's theorem, so by mean value theorem, there exists a point, x1, between x0, x, such that g prime of x1 equals 0. Yeah? Now remember, at x0, or g prime of x1 equals 0. Now at x0, we have that, so at g prime of x1, so at x1, g prime is 0, but also, so if I look at the derivative of g at x0, this is equal to f prime of x0 minus pn prime of x0 minus, now here I'm working under the assumption, so just for illustration purposes, I'm assuming n is, n is, say, bigger than 2, bigger than or equal to 2, at least from what I'm writing down right now. But if I take the derivative of this and set in and plug in x0, then I will also get 0 here. So I just get f prime of x0 minus pn prime of x0. So this equals 0. Yeah? So I have g prime of x1 equals 0. G prime of x0 equals 0. And therefore, by the mean value theorem applied again, there exists a point x2 between x and x0 such that the second derivative of g evaluated at x2 equals 0. Okay? And now I just iterate this, right? Because I still know at x0 the second derivative of g is also 0 as long as n is bigger than or equal to 2. And then I'll get that there's so there's x1 here. So let me write here. At this point we know g equals 0, g prime equals 0, and so on. At this point, g prime equals 0, and then at x2, right? So then the fact that g double prime here at this point is 0, and at 0 here we apply the mean value theorem again, and we get a point x3 in between them, where now the third derivative equals 0, and we can keep going on up until a certain point. And what point is that? That's when I've taken away n derivatives here, and all that I have left here is s minus x0. So let me summarize. Continuing in this way, we see there exists, we see for all k between 0 and n, there exists an x sub k between x0 and x such that the kth derivative at x sub k equals 0. Okay? So in particular at the k equals n stage, what do I have? So x0, x, and there's x sub n. So I'm just now going to repeat this argument one last time, and we'll see where that leads us. Since g, the nth derivative of g evaluated at x sub 0 equals 0, again, this is coming from this relation here. So let me, in fact, write that again. This is equal to f of x0 minus Pn of x0, and I'll even write out this is equal to mx x0 n plus 1 factorial times x0 minus x0. This is what happens when I take n derivatives of ns of this monomial here. So this, of course, is 0. Equals 0. So since we have that, and we have its equals 0 at this other point, there exists, by the mean value theorem now applied to g sub n, g, the nth derivative of g. So when I write mean value theorem here, I'm not applying it to the function g, I'm applying it to the derivative. So here I was applying it just to g. Here I was applying the mean value theorem to the derivative of g. Okay? And here I'm now applying the mean value theorem to the nth derivative of g. So let me make that perfectly clear. There exists a number c between x and x0 such that the n plus 1, the derivative of g, the derivative of the nth order derivative of g, so the n plus first derivative of g, of c equals 0. But what does this mean? Now, if I take n plus 1 derivatives with respect to s of this over here, I get f. Now, if I take n plus 1 derivatives of an nth degree polynomial, I get 0, right? If I take 2 derivatives of a degree 1 polynomial, which is just x, I get 0. If I take 3 derivatives of a degree 2 polynomial, I get 0. I get 0 for when I differentiate n plus 1 times an nth degree polynomial minus m, this constant again, times n plus 1 derivatives of this monomial here in S. So remember, all these derivatives I'm writing down here, these are all in terms of S, okay? Times n plus 1 factorial, and this equals 0. Right? This is just this here expressed here. And this should be C, I'm sorry. So we're plugging in C. But that means precisely that which is what I wanted to show existed. All right? So at this point C, this constant from earlier, which, remember, was defined in this way, is actually equal to the n plus 1 derivative of f evaluated at some c, so, and therefore f of x is equal to Pn of x plus c times, where c is between x and x0. Okay? So again, Taylor's theorem, says a couple of things, but it doesn't say certain things, right? The mean value theorem, as it's written, says there exists some point in between, so that the secant line from f of b to f of a is equal to the derivative of the function, the tangent to the graph at some point in between. But it doesn't, tell you that, the function near a point can necessarily, what am I trying to say? Okay, so what Taylor's theorem does say is that you can iterate the mean value theorem for higher order derivatives. But what it doesn't say is that this polynomial that you get over here, which you interpret, kind of as an approximation of the function f near x0, it doesn't say that that approximation is necessarily good, right? Because we just saw from this example that that remainder term may end up being the entire function, okay? But still, that doesn't, that's still doesn't make it any less useful in applications. Okay, so let's give a simple application of Taylor's theorem, which perhaps you, had endless homework problems or exam problems on back when you first took calculus, and we're finding critical points and trying to characterize them as relative minimums or relative maximums. We have the second derivative test, which states the following, which states that suppose I have a function from the open interval AB to R, and suppose this has two continuous derivatives on this open interval AB. If at a point in AB the derivative equals 0 and the second derivative of f evaluated at 0, x sub 0 is positive, then f has a relative min at x0. Okay? And I should say that this is a strict relative min. What's the difference between a strict relative min and just a relative min? A strict relative min, I mean that if I'm at any point other than x0 and I'm nearby, then f of x is bigger than f of x0. Okay? So let me just write that here. That means near x0 okay? In fact, let's just briefly recall what the definition of relative min is, and this will allow me to state what it means to be a strict relative min. This means there exists a delta positive such that for all x in x minus x0 implies f of x is bigger than f of x0. Okay? Okay. So this is the definition of strict relative min. A strict relative min is a relative min because what's the only thing missing from the definition of relative min is what happens if I evaluate at x0, and then at x0 we get f of x0 equals f of x0. So a strict relative min is a relative min. But it's a little bit stronger because it's saying that as long as x is not equal to x0, meaning this thing is bigger than 0, f of x is bigger than f of x0, not bigger than or equal to. Okay? All right, so I hate doing this, but the theorem stated over there. And now we need to go across the room to do the proof. All right, so f has two continuous derivatives on AB, and therefore the second derivative is continuous at x0. So since the second derivative is continuous, we get that the limit as x goes to x0, or let me put instead of x, let's say c, this equals f double prime of x0, which is positive, right, by assumption. That's what we're assuming. And therefore, by an exercise in one of the assignments, since this limit this implies that there exists a delta 0 positive such that for all 0 bigger than c, bigger than x0, and in fact we can include so let me see. There exists delta 0 positive such that for all c satisfying we get that f prime of c is positive, right? So all I'm saying is we have this point x0, x0 plus delta 0, x0 minus delta 0, and then on this interval, f double prime of c is positive. All right, you prove that, in fact, in an assignment. If the limit of a function as I approach a point equals L, which is positive, then near the point, the function has to be positive. Okay? So now I have to verify that, what am I trying to do? I'm trying to verify that I have a strict relative minimum so that there exists a delta. I have this delta 0, which ensures that the second derivative is positive on this interval. So I say choose delta to be this delta 0, and now I have to show that this delta works, meaning for all x in that satisfying that inequality, I have f of x is bigger than f of x0. So take an x between delta, within delta distance to x0. So here's x, say. Then by Taylor's theorem, there exists a c between x and x0. So here's x. There's this point c between x and x0, which I can always choose strictly in between them, such that I have that f of x equals, so f of x0 plus f prime of x0 times c minus x0 plus, no, this should be x, sorry, plus f double prime of c over 2 times x minus x0 squared. Okay. Now, at x0, the derivative is assumed to be 0, right? We're assuming the derivative vanishes at x0, and the second derivative is positive there, so this equals f of x0 plus f prime of c over 2 times x minus x0 squared. Now, on this whole interval, which is where I'm looking at, f double prime of c is positive, so this thing here is positive, and as long as x minus x0 is not 0, as long as x is not equal to x0, this thing is positive. This is a square, so this is strictly bigger than f of x 0, which is what I wanted to prove, right? So I have proven that f of x is bigger than f of x 0 on this interval here. All right? So of course, you know, the picture that goes along with this is something like, you know, let's say the point x0 is 0, at least near this point. The derivative is 0, the second derivative is positive, so this is how the function should look. Okay? Okay, so that concludes what we're going to say about differentiation. You know, I have put in the assignment, you know, kind of the most useful version of L'Hopital's rule, which is kind of the only other main thing we're missing right now from just the theory of differentiation. But remember, you know, kind of differentiation is a bit of a miracle, as I've said before, because there exist continuous functions that never have a derivative. Integration, which is what we're moving on to now, is not so much of a miracle. Because, as we'll show, every continuous function has a Riemann integral, which is a different limiting process. So all of these things we're talking about, you know, all of these notions, continuity is a notion that involves limits. Differentiation is a process involving limits, and integration is a process involving limits, but somehow integration is not as harsh a process as differentiation. Okay? Okay, so we're moving on now to Riemann, should say the Riemann integral, but I'll say Riemann integration. And so what is Riemann integration? It is, you know, you were told this in calculus, but maybe in not so careful a way. This is a theory of what it means, or this is a number that we associate to a function that you interpret as the area underneath the curve. Okay? It is not, as maybe you're told, somehow magically equal to the area underneath the curve. There is no notion of area underneath the curve. All right? The Riemann integral is a number which you interpret as the area underneath the curve because it agrees with what you think the area underneath the curve should be for simple examples. For example, a half circle or, you know, just a box. You know, these two notions agree, and therefore you interpret the Riemann integral, which is a number obtained by a limiting process, as the area underneath the curve. It is not somehow, you know, out in the universe there is this notion of area underneath the curve, and the Riemann integral magically coincides with that notion. No, it is a theory, if you like, of assigning a number that we interpret as the area underneath the curve. Okay. And it's good for, very good for, especially once we get to the real miracle of calculus, the fundamental theorem of calculus, which connects the derivative to integration. You know, it's fantastic in, you know, being able to, in its ease of computing. You know, hopefully at some point you go on to learn about Lebesgue integration, which is a much more versatile notion of area underneath the curve. and a little bit more robust. You have better theorems that you can then use and prove then use, of course. But Riemann integration is a place to start, and in fact, you know, in some treatments of Lebesgue integration, you know, Lebesgue integration is treated as the completion of Riemann integration, just as the real numbers are, you know, the completion in some sense of the rational numbers. Okay, so let's set up some definitions and notions that we'll need. So I'm just going to be talking about Riemann integration of continuous functions. This is the simplest way to go. Why not for, you know, some sense of general functions or something like that? Because, you know, in general, a function does not have a Riemann integral. So you could try to ask, can you characterize what functions do have a Riemann integral? And the answer to that is functions which are continuous in a sense almost everywhere. Almost everywhere, though, you don't know, we don't have the machinery to describe that. That's a measure theory course. So because you cannot, or at least because we don't have the machinery to fully state what it means, a precise, you know, if and only if statement about when a function is Riemann integral, I'm just going to do the Riemann integral for continuous functions, which is nice and simple enough and still pretty. So let me just introduce first some notation that I'll be using a lot. C of AB. This is going to be the set of all continuous functions from AB to R. So F from AB to R, F is continuous. Okay? Now, so as I said, that we're going to associate to an interval and a function, a number, which we will later interpret as, you know, as you know, a notion of area underneath the curve. So this process is a limiting process where we're going to be taking the domain and cutting it up into smaller and smaller pieces, and somehow writing down a number that we think approximates the area, is a good approximate area underneath the curve. So I'm going to assign some words to this breaking down process. A partition of the interval AB. This is just a finite set. X underline, which I'll write in this way, is, so it's a finite set, which I write x0, x1, x2 up to xn, with the property that x0 is equal to a, it's less than x1, less than x2. Okay? The norm of a partition, which I denote with these two vertical lines on either side of x underline, is by definition the max of the differences between these partition points. Okay? So I refer to these points that are in the partition as partition points. So this is x1 minus x0, so on, xn minus xn minus 1. A tag for partition x bar is finite set xc. So get used to some Greek letters in your life. Xc equals c1 up to xcn. So as before in the partition, we started off with a 0. Here we start off with 1. Such that each of these xc's lie between partition points. In other words, x0 is less than xc1 is less than x1. Okay? And the pair is referred to as a tagged partition. Okay, so although maybe it looks a little bit fancy, it's not. A partition is you take your interval AB and you cut it up into pieces, with your first point always being A and your last point always being B. So x1, x2, and because I can't draw n points, I'm going to draw, 4 points. x3, x4. So there's a partition of AB into, think of these points as being the endpoints of little intervals that I've broken up the bigger interval into. And the xc's are just points in each of these little intervals. So xc1 has to land there. xc2 could land in the next one. It could actually be the endpoint if we like. xc3, let's say it's the midpoint. And let's say xc4 is there as well. So, the tagged points are just lying in these smaller intervals. Okay, and at least in this picture, the biggest separation between partition points would be something like x3 minus x2 here. Okay, so the norm of a partition is the length of the largest subinterval. Okay, so I drew kind of something abstract here. Let's make this more concrete. Let's say I'm looking at, so just to write down a few examples. Let's say my interval is 1, 3, and then my partition are the points 1, 3/2, 2, 3, and then my set of tags are 5/4, just the midpoint, 7/4, 5/2. So my partition is 1, here's 2, 3/2. So those are my partition points. And meanwhile, my tags are the midpoint. So okay, and then the norm of this partition is the maximum of the lengths of these smaller subintervals here. Not the ones using C, but the one with the partition points. So max the 3/2 minus 1, 2 minus 3/2, 3 minus 2, and is 1. The length of this subinterval. Okay?
Okay, so now given a tagged partition, we're going to associate a number to this tagged partition, which we interpret as an approximate area.
So let f be a continuous function, xc a tagged partition. The Riemann sum associated to
I should say of f
associated to the tag partition xc is the number s sub f of x bar, x underline xc underline, which is the sum from k equals 0 to k equals 1 to n of f of xck times xk minus 1. Okay?
So again, what we interpret this number at, so how do we interpret this number? We interpret it as somehow, we give meaning to this number as an approximate area, right? If this is AB and there's a function f, and let's say those are the partition points, so x1, x2, x3, so x4, x0, and let's say the tag are just the right endpoints of each of these smaller intervals, then what is this number, at least in terms of this picture? Okay, that's a little off, but anyways, so what I've shaded in, this area, this equals this Riemann sum of f associated to this tag here. And let me go over again the graph of f. So, you know, this number here, which we've come up with, we interpret as somehow being an approximate area. Again, I don't like saying area underneath the curve because that presupposes that there is a notion of the area underneath the curve independent of what we're doing here. But that's not the case. We are, in fact, giving a theory, a mathematical theory of area underneath the curve. All right? We are prescribing a number which we interpret as the area underneath the curve. So these Riemann sums we interpret as being, you know, approximate areas. All right? And so what we would like to do is somehow take a limit as the lengths of these subintervals get smaller and smaller as the norm of the partitions go to 0. And what we would like to say is that these approximate areas, these are just numbers, converge to some limiting number, a, say. That number we refer to the Riemann integral, we refer to as the Riemann integral of f, and we interpret as the area underneath the graph of f. Okay? Now for this to work, we have to show that as we take partitions with smaller and smaller norm, where the intervals get smaller and smaller, these approximate areas actually do converge to some number. And that's going to be the content of the next lecture, in which we'll prove the existence of the Riemann integral and do some properties about. But so the take-home point is, again, there is no definition of area underneath the curve independent of what we're doing. It's not like out there in the universe there's a notion of the area underneath the curve, and when we compute the Riemann integral, magically those two things, those two numbers coincide. No. We are constructing a theory of the area underneath the curve, which, for example, for a half circle or square or ellipse, do in fact coincide with stuff you know from ordinary geometry. Okay, and therefore it gives a good theory of area underneath the curve. But in order for us to construct that theory, or how we're constructing that theory is, for a continuous function, we define a number associated to a partition, which we interpret as approximate areas. We would like to say these approximate areas converge to some number as the partitions get finer and finer, or as the norm gets smaller and smaller. And that limiting number we interpret as the area underneath the curve. And so that'll be what we do next time, is actually show the existence of this limiting number, which is the Riemann integral of f. And we'll stop there.